and it is a pleasure to be here to share some of our results on physical therapy and outdoor assistance with the Myosuit. Before I start, I would like just to say that I'm here giving the presentation, but most of this work was done in close collaboration with Florian Haufe, who has graduated and moved to another NCCR project, actually. Okay, so most of you do know the Myosuit, but for the sake of clarity, I will reintroduce it again, starting quite broadly from the field of exoskeletons. When we talk about exoskeletons, we imagine something like what we see here on the left side of the screen, where you have a rigid components and electric motors with mechanical links to deliver assistance to the human body, maybe providing even the entirety of the power and the torques needed to complete a task such as walking. But the reality is that most patients don't need full assistance. Indeed, as you can see here with the bar on the bottom of the screen, there is a wide range of needs from patients. So there are patients who indeed need such as exoskeletons, but there are also patients who are capable of independent walking and might benefit simply from a pair of crutches. And when developing the Myosuit, I wasn't around, but the rationale behind the design and the requirements of this system was to try to bridge this gap between people that can walk independently and people that cannot walk at all. And at the time when starting this project, there was actually no device, no exoskeleton, no wearable device known to us that could do this. And so this is where the Myosuit is positioned if we look more broadly at the field and at the needs of patients with motor disorders while walking. And what you see here labeled as transparent behavior is something that I will introduce in a bit more details later, but is fundamentally the ability of the robot to transition from a modality where it can deliver assistance and support walking to a modality where it can simply get out of the way so that the user feels like he or she is not wearing anything at all. And this is very, very different, as some of you, very difficult, as some of you may know, to do with rigid exoskeletons. So let's introduce the Myosuit. It is now a commercially available product sold and certified for the European market and produced by Myoswiss. Myoswiss is a spin-off from our lab initiated by Kai Schmidt and Jaime Duarte with help from NCCR. So it was actually one of the very first spin-offs from NCCR Robotics. The way it works is that it has this kind of backpack structure that you can see here on the left with an interface display for the user to change modality and to activate assistance. And then it has two tendons that are here labeled as tendons and that move from what we call the tendon driving unit located on the trunk, on the back of the hip, and then on the side of the knees of these plastic orthoses that you see and that wrap around the knee. It also has two inertial measurement units to understand in what phase of walking the user is, segment the steps, and recognize gait events such as heel strike and toe off. So for a more thorough understanding, this is how the Myosuit assists walking. What you see here is the gait cycle, starting from 0% corresponding to a heel strike to 100% corresponding to heel strike, the subsequent heel strike of the same leg. And usually the walking cycle is separated, is segmented into the stance phase and the swing phase. In the stance phase, the leg is supporting the weight of the user. In the swing phase, the leg is brought forward for the next stance phase. What you see here as tendon force in the bottom plot, labeled as tendon force, is indeed the tendon delivered, is the force on the tendon of the Myosuit. So the Myosuit indeed recognizes heel strike here at 0%, has a delay of a few milliseconds, and then tensions these artificial tendons, applying an extending moment on the hip and the knee and preventing the leg from collapsing. So you can see it here. When the left leg heel strikes, the tendons that is partially visible and that basically is routed along the glutes is tensioned and supports the leg in the stance phase of walking. We define the Myosuit as an external layer of muscles. So instead of an exoskeleton, we like to call it an exomuscle. And when talking to patients or when trying to explain is there a working principle to therapists, we like to say this. It is a bit like an e-bike for walking. And the analogy comes from the fact that the user still needs to initiate the walking movement, just like you still need to initiate pedaling on an e-bike. And then the device will give you some assistance, but it cannot replace the entirety of the torques or of the power needed for walking. So one of the first studies that we did, and this was now about 1.5 years ago, was trying to understand more in depth what the biomechanical effects of such a device are on human movement. And we started with healthy subjects. So I said before that the Myosuit actively assists weight bearing through the mid-stance phase of walking. So it extends the legs and works in parallel with the glutes to extend the hip, and with the knee extensors to extend the knee joint. So in this study involving 10 healthy participants, we looked specifically at the activity of these muscles, and we tried to quantify the effect of the Myosuit. So this was a mirror design in a form ABBA to avoid potential odor effects. And we had the Myosuit off in the A conditions and the Myosuit on in the B conditions. It was about 10 minutes of walking in each conditions, and we looked at some muscles that are responsible for power at the hip and knee, including, for example, the gluteus maximus. And we observed that in this mid-stance phase of walking, highlighted here with a gray area, there is indeed a drop in the activity of the gluteus maximus of about 30% of its value in the no condition, in the off condition. Very similarly, the muscles that extend the knee are affected by the assistance from the Myosuit, even in a more substantial way. So what we see here is the vastus medialis, responsible for knee extension. And similarly, during the next step, the rectus femoris. The rectus femoris is a biarticular muscle that supports both hip flexion and knee extension. And also this muscle in these healthy participants was substantially and significantly reduced during the stance phase of walking. Now, once we understood or we quantified a bit more in details what were the biomechanical effects of the device on healthy participants, we formulated a hypothesis, which was that if this device can indeed work successfully in parallel with the muscles responsible for hip and knee extension during the stance phase of walking, then it can be useful for a population of people with motor impairment, and specifically people with weakness in the hip and knee extensors. But another big advantage of this device is that it can not only be used for rehabilitation, but it is lightweight, it is only 5 kilograms, it is easy to use, and it is extremely portable. So we carry it from one place to another just in a backpack. And so unlike traditional exoskeletons, we can hypothesize that this device can not only be used in a controlled environment in a rehabilitation clinic, but also in activities of daily living, in more unstructured environment, for example, outdoors. So we started with the first hypothesis. So how good is the Myosuit, or what are the benefits of the Myosuit in a physical training protocol in a controlled environment? And for this, we enrolled 12 participants with a variety of conditions affecting their motor abilities, ranging from multiple sclerosis to incomplete spinal cord injury, muscular dystrophy, and stroke. And these people went through 5 sessions. One session was used for familiarization with the Myosuit, and 4 training sessions where the Myosuit was used for a series of physical exercises, very similar to the ones that you would find in traditional therapy, and then some assessments. So here are the assessments. We specifically ran clinical assessments that are known to the field, such as a 10-meter walk test. For some participants who could do it, a 2-minute walk test. So basically this is walk as much as you can in 2 minutes, or walk as fast as you can in 10 meters. Additional exercises included sit to stand transfers, balance trainings, and even steps. This was done in collaboration with Myosuit at their physiotherapy center. So we had 12 participants. 8 participants completed. We had 12, yeah, 8 completed the therapy. Some dropped out, and 5 of the 8 who completed had a substantial increase in walking speed. So this is a person with hemiparesis after stroke. And we saw an increase from 0.59 to 0.7 meters per second. So one of the main outcomes of this study was that training with the Myosuit is possible for a wide variety of speeds, so of abilities of the patients, but also for a wide variety of conditions. So we have here quite a versatile tool. And indeed, different speeds of walking. So what you see in the left is a 0.2 meter per second walking. What you see on the right is someone who would walk as fast as we do, up to 1.6 meters per second. And when I mentioned that 5 of the 8 participants improved their walking speed throughout the sessions, this is the data. So what you see here and on the y-axis is the net change in walking speed, where 0 would be the change at baseline during the familiarization session. And then we had the 4 training sessions after that. And you can see that there is a common trend, and 5 of the 8 people had a walking speed after the 4 training sessions that was above their baseline. So training with the Myosuit is feasible. It is a versatile tool for physical therapy, and most participants improve their walking speed throughout the training program. Now, why this happened, we do not know. And this is why I asked the question to Matteo at the beginning. We think, or we can speculate, that there might be 2 mechanisms at play here. One being adaptation to the device. So it could be that the participants learn to use the device better throughout the sessions. And the other explanation could be simply the effect of training. These were all chronic patients, so it could be that simply the fact of having a training session at all improved the physical performance. In this feasibility study, we did not have the possibility of investigating or going in depth to answer these questions. But the other interesting application of the Myosuit, as I mentioned before, is outdoor assistance. So using the Myosuit to assist walking in more unstructured environment. And since we're in Switzerland, of course, the most obvious outdoor activity is hiking. And so we had a very brave participant with incomplete spinal cord injury, level C5, who volunteered for a walk in the Swiss mountains. We had 4 time-bounded tests, 4-minute tests on an outdoor sloped mountain path in Erisau, and again, a protocol that followed ABBA design to account for potential odor effects, where in the A condition, the participant was wearing the Myosuit, and in the B condition, the Myosuit was providing assistance. And so I will directly jump to the results. And this is what they look like. So in the panel on the left, you see the person without the Myosuit. And we were here measuring metabolic cost of walking through a mobile respirometer. And in the right, the same participant with the Myosuit. And what we observed was a 30% increase in walking speed and a 9% decrease in metabolic cost. So this means that the Myosuit allowed the person to walk faster and substantially faster and consuming less energy. So this same person was more efficient while walking with the Myosuit than without. To gain a bit more insights, we also asked the same participant to perform an indoor session here well, it was in Baugrist, where we have a motion capture system and an instrumented treadmill. And we analyzed his kinematics, finding that wearing the Myosuit results in a more upright posture and a higher cadence of walking. So from these studies are definitely not conclusive, but they do prove the potential of using this very versatile, portable technology in a variety of different conditions. And what we're most excited about is that they prove that this technology can be used in an unstructured environment. So we can go outside of the lab, we can move in nature, in daily domestic environments, and improve people's mobility in people's life. So just to sum up, the main conclusions from these two studies were that the Myosuit is a feasible tool to support both physical therapy and outdoor assistance, and that lightweight devices such as Myosuit could be used to improve mobility in daily environments and ultimately the quality of life for people with walking impairments. This is just a teaser on a study that we are starting now in collaboration with the German Heart Center. And this is a study on people with chronic heart failure that we are very, very excited about, because this is a huge population and cardiovascular conditions have a huge impact on people's quality of life. So the device is already there, and we have already started part of the study. Specifically, we have finished the uncontrolled feasibility study with 30 participants, and we're now on our way to start a controlled efficacy study to evaluate the effects of the Myosuit on physical therapy before and after heart transplant. This brings me to the end of my talk. Thank you for your attention, and I'm happy to answer questions.